Hello everyone. We are going to discuss one of the most fundamental and important concept in operating systems today. This is called as critical section problem. Let me begin with a simple question. When multiple users or processes wants to use the same resource at the same time, what happens? Think about it. Will everything work smoothly or will chaos happen? Exactly that chaos is what we try to avoid using critical section mechanism. Let me take example from money heist. Let me connect this with money heist scenario. That was a web series, correct? So imagine there is a gang inside the Royal Mint in money heist. We know that there was only one vault door control system. If Tokyo, Berlin, and Nairobi all try to control it at the same time, the system will fail. The plan collapses. So what do? Only one person controls the system at a time. And that is exactly what we call as critical section problem. Same case, like if I talk about labs in our department, when multiple students access the shared server or a database, only one should modify the data at a time. Otherwise, the data corruption can occur. So let us begin by understanding this situation very carefully and in very practical way. Imagine a department like PUCSD, where academic work is happening continuously throughout the day. Professors are printing lecture notes, students are submitting assignments, administrative staff is printing important documents, letters. All of these activities depend on one common device which is kept in the office, and high quality shared printer. Now, this printer is not owned by a single person. It is used by many peoples. And that is why we call it as a shared resource, which means a resource that is accessed and used by multiple users or multiple programs at the same time. Let us slowly think about completely this situation. At a single moment of time, one professor may be printing, say, 20 pages of lecture notes. Another professor may be printing an exam paper. A student may be printing a last minute assignment. Someone else also may be trying to print something. All these requests are coming to the same printer. Now, here is the key question. How does the printer decide whose job to do first? What happens if all requests come at the same time? So if there is no proper system to manage these requests, then confusion will happen. Print jobs may overlap, data may mix, and the final output may not be correct. So from this simple real life situation, we understand a very important idea. So when many users try to use one shared resource, we must control access properly to avoid problems. And this idea forms the foundation of critical section problem, which we are going to study in detail. Let us move deeper into this problem statement and understand what exactly can go wrong. So when multiple users or processes try to access the shared printer at the same time, the system may behave in an unpredictable and incorrect way. And this situation is called as race condition. So let us understand this term very clearly. A race condition occurs when the final result depends on timing of events, meaning which processes runs first or the process runs first and how fast it runs compared to others. It is like a race between processes where each one is trying to compete with or complete its task before the other. Let us consider this two professors here from the department. Professor HV wants to print 10-page document. Professor KN wants to print a 5-page document. Ideally, the printer should complete one job fully and then it should start the next. But if there is no proper control, the printer may start processing both the jobs concurrently at the same time. So the output may become something like this. Say, for example, first 5 pages of HV, then 5 pages of KN, and then remaining 5 pages of HV back. Now observe this. The order is completely disturbed. The output is mixed and incorrect, and document loses its meaning. And this is not the small error. This is a serious failure in the system. So the main problem here is not the printer itself. The problem is when multiple processes are running independently, there is no coordination between them, and their interference with each other is causing the problem. And because of this, the final result becomes unpredictable. So race condition is situation where lack of proper coordination leads to incorrect results. Think of two people writing on the same whiteboard at the same time. One writes half sentence, the other writes something else in between. The final message becomes confusing. And that is exactly what happened in this condition. So let us define the critical section. Right? What exactly it is. So A critical section is a part of program where a shared resource is accessed. So let us connect the same example which we talked about earlier. When a process sends a print command and the printer processes that job, and these two actions form the critical section because they involve direct interaction with the shared resource. At any point of time, when we say critical section, the fundamental rule says at any point of time, only one process should be inside the critical section. So if one process is using shared resource, all the other process must wait until it finishes. Why we require to apply this rule? Because if two or more processes enter in the critical section at the same time, their operations may overlap, data may get corrupted, and the system may produce incorrect output. And this leads to serious system failure. So let us try to understand how why there is a need for control and synchronization. We already know that multiple processes exist. Only one should enter at the same time for the critical section or in the critical section. How do we enforce this rule then? So we need a proper mechanism that ensures only one process enters, others wait properly, and everyone eventually get a chance. This mechanism is called a synchronization. So synchronization means coordinating multiple processes in such a way that they work together smoothly without interfering with each other. So good synchronization system must ensure three important conditions like mutual exclusion. Only one process enters in the critical section. Progress. If no one is inside, someone should be allowed to enter, and no process should wait forever. Like that is bounded waiting. So think of a traffic signal. So red, that means stop. Green, that means go. This controls the movement of vehicles and prevents accidents. Similarly, synchronization controls processes and prevents conflicts. Now, to find a solution, like if I try to compare with our problem, when one professor is printing, no other professor can print at the same time. Progress, if no one is printing, someone wants to print, then that process should be allowed. And then bounded waiting, there must be limit on how long a professor can wait or has to wait to print after submitting their job, resulting in no indefinite waiting. So if the process waits for a long, then that results to starvation. Okay, so let us give a solution for this two professor approach. So this solution is called as Peterson solution. This is designed to solve critical section problem, but uh, one important aspect here is like this algorithm works only for two processes. Correct. So they respect both the process here communicate with their intention. They respect each other's turn, and only one enters at a time. Correct. Now, when we say this, ultimately, what exactly happens? Each process says, I want to enter, then it gives a chance to other. And if other is also interested, one waits. If not, then enters. So to control this, we would be using two important variables, which are shared variables between both the processes. First is flag. Flag is a Boolean variable, Boolean array, one can say, for both the processes. So it will have value true. That means I want to enter into critical section, and false. That means I do not want to enter into critical section. And this shows the intention. The flag variable would be showing intention. The turn variable, this variable decides which term it is to enter. So if we see, it would be like this. Right. So here, like flag I equal to true. That means professor wants to show the intent, or professor is showing the intent. He sets turn equal to j. He lets the other professor know that it's his turn if he wants to print. Now wait, if the other professor wants also to print, then that flag j, he already had true. You are saying turn equal to j. That means the professor is permitted to print. He finishes the printing, then ultimately that happens. So when, if you see, this critical section is divided into three parts: entry section, critical section, and exit section. Entry section would be you are setting your intention. Okay. Then when the process permitted to enter into critical section, that is print option, and then exit. So to understand this, I would be introducing you through a C program. Okay, which would be like between this would be done for two processes. So let me go back and write. Sorry, I should write. So let us write this code. Let me include header files, hash include. So we will be requiring approximately 5 to 6 files because we would be considering processes, 2 processes. So stdio.h, then stdlib.h, uni std.h, okay, then stdbull.h, then sys/wait.h, then sys, as we are going to make use of boolean variable, so that's why we have to write stdbull. Yeah, we wrote it stdbull. Then as we are going to make use of memory to be shared, so I would be using mman.h. So now the shared variables are, we said turn, and then we said boolean flag. Correct. So this again is a pointer. Fine. So let us write first the critical section, void critical section, and we'll have the name to whom it is permitted or it is permitting printing. Correct. So we'll write here printf %s is printing. That means this is a critical section. He is or the professor is permitted to enter into critical section. /n, then m. Correct. Now when we have to show that work is going on, so that's why we'll simulate that printing option by providing sleep. Then professor s has finished printing /n. Correct. This is done. So we have here critical section. Now Peterson solution we have to write. So void Peterson. So we'll add first the term I, and then the name to whom we are going to permit the printing. Correct. So now our code for Peterson. So we'll write j equal to 1 minus I to set the term for the other professor. Now let us write the entry section. So I will write here entry section. Entry section is what? You have to set flag of I equal to 2. Show that you are interested. TRUE. Then you set turn for the other professor. This is entry section. Now we have to check whether the other professor is interested or not. So flag j and add star turn equal to j. So this would be continuous check. So if it is not, then we would be permitting this professor critical section with the professor name. This is critical section entry. Okay, enter into critical section. Enter into critical section, and then exit section. Exit section. Correct. So this is exit section. So exit section would be what? Set the flag I, because you are done with your printing. So flag I equal to false. Now important thing here, we are going to make use of two you can say system calls. Like one is mmap, another one is unmap, memory unmap. So if I write man map, mmap, and unmap. Now these functions are responsible for this mmap system call is mapping for a file or memory region into the process address space. Correct. So one can see that there are say parameters to mmap. So first is address, starting address. This starting address. So usually it would be kept as null. So if null, that means OS decides where to map. So we will be keeping that null. Okay. Normally you should keep it null. Then length, size, how many bytes you want to map. Correct. Then third, port. this protection, there are common options available like protection read, protection write, protection exec. You can see below information about them. Correct? The protection flags. Correct. Now, like protection read, can write, and can execute kind of thing. Then there is an option called flags. Okay, these flags would be like either it will be map shared or map private. Then FD, the file descriptors. Okay, if at all this would be obtained through say open. Now, suppose if you don't want to make use of file, then you are going to write this map there, like you can see below, or flag, correct, map private, map shared, correct, and then this. So if you are you want to make use of it for say it is not backed by file, then you have to make use of anonymous. So if it is anonymous, then the next parameter that you are going to have here for FD, okay, that would be kept as -1, correct. And then lastly, the offset. Offset would be like you are going to make use of offset. Okay, you can put that value depending upon what exact is. This would be kept as 0. Usually, that is the start address of the file. Okay, usually 0. So this would be returning. If success, it returns the pointer, and if error, then failure. Then similarly for unmap, the whatever the pointer that you got, that would be address, and then the number of bytes that you used. So let me go back and check out the code again. Fine. So let us go back here. Now we have to write that code. Correct. So mmap. So I will write for turn. This is a shared variable. Mmap. Correct. Then are using null. Okay. Then this is an integer. So size of integer. Then we will write protection read. And we want it to be read and write. So that's why read write. Okay. Then we will use map shared, the flag. Okay. And we want it could be shared or anonymous, because we want that for -1. That needs to be, because we don't want to use the file. Okay, that's why. So you write here and anonymous. ANONYMOUS. Yes. And then, as I stated, when we are using anonymous, then this should be -1 and then started. So this is done for first variable. So let us check. Yeah. So you can check this, like whether the bracket is properly written. Yes. Yeah. Now this is for Boolean. Correct. The flag. Flag variable. This would be Boolean. So it is an array for 2 processes. So that's why. Correct. Now, before, as we are going to make use of 2 processes, so I will set these values for flag 0 and flag 1 equal to initial value to be false for both, and value of another shared variable turn equal to 0. Now let us create processes PID underscore T. So PID professor 1 and professor. Fine. Now we have to write for professor 1. So prof 1 equal to fork. Professor 1 given chance. So if professor 1 is equal to 0, that means it should enter into critical section, like he or she is permitted. We are going to make use of some code. So our function name, you can check the function name. So we have said Peterson, capital P. Peterson, correct. Then we are going to write its turn, then his name, Professor HV, slash n, double quotes, semicolon, correct. And then once the critical section is executed, terminated. Similarly, we have to write it for Professor 2. So this is for Professor 2, Professor 2, Professor, sorry, here it will be 1, then other professor names, Kn, correct. So Professor Kn is given a chance. Now, as we are using fork, So that's why we'll write wait null, because parents should not terminate. That's why both the children should first complete. Now once done, so we have to unmap. Unmap. What is to be unmapped? So the turn variable, size of it is integer, bracket complete. Then next is your flag variable. Flag. This is size of 2. So that's why 2 multiplied by size of, correct? And then return 0. Hopefully this program is correct. Let us compile this and check whether it is really not having any error. So GCC dash of 32. Okay. So line number 3, 57. Yeah, this was we forgot to write this for critical section. So done. Let us execute. Professor HV is printing. Correct. So let us check the code. I hope we added sentence is printing. Sentence has finished. Let's compare it again. Professor HV is printing. So you can remove this lesson from here so that you can check again. Now you can see first professor would be given a chance. HV is printing. That means he is permitted to enter into critical section. Then HV finished. Then KN finished. Correct. So that's how the simulation can be done. So let me go back to my presentation. Now, when we saw this implementation exactly for the processor, let us understand what are the limitations. So as I stated, we used here two system calls earlier. So the limitations here are this works only for two processes. Okay. In real systems, there might be hundreds or thousands of processes. So this solution becomes insufficient. The second limitation is it is not scalable. It is difficult to extend this logic to many processes. And practical issues here are modern systems require more efficient and flexible mechanisms. So when to handle this real world complexity, we can use multiple solutions. Like for example, for larger departments with multiple professors and students, more advanced synchronization mechanisms like which would be learning after a while, mutex, locks, semaphores, monitors can be the solutions. Fine. Now let me conclude and bring everything together with respect to the topic that we had understood. The critical section problem is about managing access to shared resources in a safe and controlled manner. Right? Ensuring that multiple processes do not interfere with each other. So without proper control, why this is important? Without proper control, systems become unreliable, errors occur frequently, output becomes incorrect. So with proper control, we can have systems behaving correctly, correct? Data remains consistent and users get fair access. And this concept generally can be seen used at multiple places like operating systems use this, banking systems, ticket booking systems, database management, cloud platforms, and so on. So students always remember this every time. Whenever multiple processes share a resource, discipline and control is necessary. So without synchronization, systems become chaotic and unreliable. So with proper synchronization, systems become stable, predictable, and efficient. So next time we'll be talking about next video would be talking about same Peterson solution, but in that case it would not be with processes like process. That definitely it will be with the processes in terms of threads, but not in terms of the process created using fork. Thank you.